Okay, we just started to get viewers for the office hours, so I think I'll start. Let me get organized here real quick. And then hang on a second.
Hey, I'm sorry, I have a thing I've got to be doing right now. Oh, okay. Can I leave back with you a little bit later on today? Is that? Actually, I thought we were at 10 today. Oh, okay. I'm sorry. Was that wrong with that? I don't know. That's a lot of fun. Oh, I'm sorry about that. Okay. All right, so just reschedule again. Yeah, I really apologize. I had it on my calendar for piano. Sorry. Sorry. Okay. All right. Let's see. I'm on a conference call right now. Okay, sure.
All right, sorry about that. Okay, so I'm just going to start taking some questions in turn. Okay, so I'm answering this question from Rui. So it says, when should I use alpha or z1 minus alpha? And could you give the general formulas and R codes for calculating a p-value? Let me answer this question kind of very generically first, and then it looks like there's some specific questions about some of the quizzes. Let's see. So how do I do a screen share? Okay. There we go. Okay. So remember, when we're talking about the normal distribution, right, the alpha quantile and the 1 minus alpha quantile, here I'm assuming alpha is less than 0.5. The z alpha quantile is equal to, here's the z, 1 minus alpha quantile, is equal to the negative z, 1 minus alpha quantile. Okay? So if you're, so I think that the crux of the question is, which quantile do I use in which setting? So notice if you do a confidence interval, you know, let's say you do a t confidence interval and you have x bar plus or minus, I always say z 1 minus alpha over 2 times the standard error, s over square root n, square root n. Okay. Here in this case, let's just let me just put alpha tilde here, and just assume that alpha tilde is equal to alpha over 2. Okay? And notice in a confidence interval, if we plug in, so here, here's alpha tilde. I'm going to switch everything to an alpha tilde, remembering that when we do a confidence interval, we divide alpha by 2. Okay, so if I were to plug this guy in, right, I would get this interval. If I were to plug this guy in, right, I would get x bar plus or minus z alpha tilde s over square root n. And then because this guy we just wrote down is equal to the negative of this, right, it's symmetric about 0. So if this is the positive number, when I flip it around, it's just the negative of that number, okay? Then this guy right here is going to be equal to x bar plus or minus negative z 1 minus alpha tilde s over square root n. And then just manipulating, that's just x bar, I guess, minus plus z 1 minus alpha tilde s over square root n, and we just tend to prefer to like to write our confidence interval with the higher number up top, so it's plus minus. So in other words, it doesn't matter in a confidence interval which one you put in, you get the same answer. You just may have accidentally screwed up the order of the two things. In a p-value, it does matter. In a p-value calculation, it does matter. So let me get rid of this. Or here, I'll just move to the next page. Oh, do I not have a next page? Page, no, I want pages, and I want, how do I do it? File, edit, insert page, there we go. Append page, there we go. Let's add, I'll add 10 of them. There we go. Okay, now for a p-value, okay, let's now look at it this a little bit differently. Suppose we have a test statistic that works out to be, well, let's just leave it like that. We have a test statistic, and we're testing h naught, whether or not the, you know, whatever's in the numerator of the test statistic, let's say mu equal to something versus HA, mu greater than something. Let's just put it 0 for a specific context. Okay, then you have your test statistic, and when you calculate your for example, your p-value, right, you want the probability of being at the test statistic or larger, right? So if this was a normal calculation, it would be p norm of our test statistic in R, with, you would have to put in mean. You don't actually, it assumes this, but let's just put it in anyway. Mean equals 0, variance equals, or SD equals 1, in the event that this test statistic follows a normal distribution under the null hypothesis. If it follows a t-distribution under the null hypothesis, you would put pt there. If it followed a whatever distribution, you would put that whatever there. Okay. And then if you wanted to test less than, right, your test statistic would likely be over here, or it doesn't matter where your test statistic is. If your test statistic's way over here, right, either way, because you're testing less than, right, more extreme evidence in favor of the alternative would be whatever is less than your test statistic. So then you would want, oh, and I'm sorry, I left out a little bit of the R code here. Here you want upper dot tail equals true to make sure you get the upper part of the distribution. Here now you want the lower part of the distribution, so you would do the same thing, but you would omit that upper tail statement, and that would give you the lower part. Okay, so that talks about how do you calculate the p-values. Okay, and this is a particular case for the normal or the and so in that case, there is no alpha to compare to. Once you calculate your p-value, I'm sorry, there is no normal quantile that you have to get if you're calculating a p-value. You just then compare it, take your p-value, p, and you compare it to your alpha level. If you take your p-value p and you compare it to your alpha level, and if your p-value is less than your alpha level, you reject. If it's greater than your alpha level, you fail to reject. And if you're doing a two-sided test, you double your p-value before you do that comparison. Okay, so for p-values, then there's no concern over whether you're using z1 minus alpha or z1 minus alpha over 2. Okay, finally, to get to the final part of your question, what if we're testing these things and we're doing a rejection region? So we want to take our test statistic and compare it to a normal quantile and ascertain whether or not we've achieved statistical significance. Well, if we're testing greater than, then we want to test whether our test statistic is bigger than some cutoff. And so think about it this way. If our test statistic is, let's just put in particular context, our test statistic is x bar minus mu over s over square root n. If our test statistic is that, and hopefully you'll be able to extend the principle, imagine if we want to test greater than, okay? So we want to we want to find a region so that the probability under the null hypothesis of the test statistic being larger than it is alpha %, okay? So if we want to test greater than, let me get rid of my test statistic there. Okay, if we want to test greater than, well, we know that if we set the, if we calculate this probability here, where this is z1 minus alpha, that will leave alpha up in that tail there, and that will leave 1 minus alpha in the lower part of the tail, okay? And so test statistic bigger than z1 minus alpha under the null hypothesis, that probability under the null hypothesis will be alpha, okay? So if we compare our test statistic to that quantile under the null hypothesis, the probability of rejecting will be exactly alpha. So we will have achieved, if we set alpha equal to say 0.05 or something like that, we will have achieved the statement that the probability of rejecting our null hypothesis under the null hypothesis is small, okay, and that, or in other words, we will have achieved having a type 1 error rate that is low. So if we're testing greater than, we're going to set our quantile as the upper quantile, z1 minus alpha. If you were testing less than now instead, right? And notice, by the way, I also, this is kind of an interesting little fact, right? Another thing we could have done and still had a type 1 error rate of alpha. So let's imagine that we're testing the alternative as this hypothesis. Imagine if we did set our rejection region to be z alpha and lower. So just to remind us, you know, if z alpha is, if alpha is 0.05, then this is negative 1.28. and if it's 0.95, it's positive 1.28. Okay, just for a particular instance. Okay, so imagine if we set it there, but we're testing greater than with if we set our rejection region as this region. Well, let's look at that probability. That's the probability our test statistic is less than Z alpha under the null hypothesis. Under the null hypothesis that mu is 0. And here I have mu naught in there. Under the null hypothesis, right? That will still be alpha, actually. So whether we reject, it turns out that our type 1 error rate will hold whether we reject for the large value or the small value. But the problem is, here, the power would be very bad. The power would be really bad. So that's what you screw up if you use the wrong one of these things, if you use the wrong quantile when you're doing a rejection region. Okay, you screw up the power of the test, but you actually have the correct type 1 error rate. So let's just put in a context. So imagine if you want to test whether or not a mean is 5 or something like that, right? You want to test whether, I don't know, whatever the average height is 5 foot, 5'5" or something like that. Okay. You want to test whether the average height is that. Okay. And you and let's say if the hypothesis is, your test is, let's just say 5 to make it easy. Your test statistic is going to be x bar minus 5 over s over square root n, right? And so if you set it to this guy, you'll reject if your average height is bigger than 5 feet, right? Much bigger than 5 feet. If you set it to this guy, you're going to only reject if your height is much smaller than 5 feet. And it turns out that yields the correct type 1 error rate, but of course you're going to have more power, a lot more power if you do the correct one-sided thing. So anyway, to answer your question, Rui, the only way in which, the only time in which, as we discussed already, accidentally messing up whether you put in Z alpha or Z1 minus alpha, it doesn't mess up a confidence interval. And then for a p-value, it doesn't matter because you don't actually need the normal quantile for a p-value. However, the one time you do need it is when you're performing a rejection region. You're calculating a test statistic and you're comparing that test statistic with respect to a normal quantile. Then you need to pick the normal quantile that is consistent with your alternative hypothesis. Okay? And then there's only a couple of rules you have to follow. If it's less than, you're going to pick the lower quantile. If it's greater than, you're going to pick the larger quantile. And if the test is two-sided, you're going to pick you want to make sure you get the alpha over 2 quantile, and you want to compare the absolute value of your test statistic, i.e. throw out your test statistic sign, and then take the positive one of the Z1 minus alpha over 2 and Z alpha over 2. Okay, so that's the only rule. So if you're testing less than, use Z alpha. If you're testing greater than, you're going to use Z1 minus alpha. And if you're testing not equal to, you're going to use Z1 minus alpha over 2, which is the positive one. And you're going to take your test statistic, and whether it's positive or negative, you're going to throw out the sign and compare it to that. I think that covers the whether or not you use Z alpha or Z1 minus alpha. There is one caveat, and let me just say there's an instance where it's easy to mess this up. And the instance where it's easy to mess this up is when you're testing H0 mu1 equal to mu2 when you have two groups, and HA, say mu1 less than mu2, or versus HA mu1 greater than mu2, or another alternative would be HA mu1 different from mu2. Okay, so here's the three alternatives. So in this case, it's less straightforward because it depends on how you form your test statistic. If this is your hypothesis test, right, then if you write your test statistic as x bar 1 minus x bar 2 over the standard error of x bar 1 minus x bar 2, okay, if you write it like that, okay, then you're going to want to reject if this test statistic is small. Okay, right? If this happens to be your hypothesis. However, if you form your test statistic as x bar 2 minus x bar 1 over this standard error, okay, then you're going to want to reject if this test statistic is large, if you're doing that hypothesis, right? Because the direction of the alternative would be x bar 2 being larger than x bar 1, okay? And so in this case, the test statistic would be positive. In this case right here, the test statistic would be negative in the direction of the alternative. X bar 2 would need to be, x bar 1 minus x bar 2 would need to be negative in order to be supporting the alternative hypothesis. Okay, so there's an important distinction in these cases. Anyway, that one's easy to mess up. That kind is easy to mess up. I would mention, I think in one of the quizzes, I had accidentally, when I was doing the solution, I put a quantile of 0.95 for the normal, and I think I mistakenly forgot to include the 7. So instead of 0.975 for the normal quantile, I did 0.95 for the normal quantile, and it wound up getting screwed up. And so it wound up the answer being correct for a 90% confidence interval instead of a 95% confidence interval. So I'm wondering if that's actually the root cause of some of this confusion. It's corrected now. However, that might have caused some confusion. So at any rate, I hope that answers your question about whether to use z1 minus alpha or z1 minus alpha over 2. And let's see, could you explain the question 2, 3 of quiz 2 in boot camp 2, and question 8, quiz 1, and of inference. Okay, so I'll try and do some of these. Let me try and do some of these. Let me get the inference one first. So let's see, what did you say? Question 12. All right, and question 8 of quiz 1. Okay. Oh, question 8. Oh, okay. Why don't we all see if I can find it. I have a practice problem. Let's see. So hopefully people have looked at these practice problems. I'm working on. Oh, I lost where? Yeah. Hopefully people are looking at these practice problems. I've kind of almost got the second one done. Let's see. And then let me see. Okay. So I think I got a nice practice problem. Let's work through that. Oh, and by the way, in these slides, if you sometimes it messes up the math rendering. I don't know, that's some sort of interaction between Slidify and MathJax. Just hit refresh the page, and it usually corrects it. Okay, so let's look at this distribution right here, and we'll do it in R. Let's see. So the probabilities here in this case are 0.1, 0.2, 0.3, 0.4. Let's double check and make sure there's a valid PMF, because it would be just like me to give an invalid PMF. Okay, so it's 0.1 plus 0.2 is 0.3, 0.3 plus 0.3 is 0.6, 0.6 plus 0.4 is 1, so that adds up to 1. So the probabilities are all greater than 0, they sum up to 1, so it's a valid PMF. Okay, then X, the possible values that the probability can take, is 2 to 5. So that means it takes value 2 with probability 0.1, value 3 with probability 0.2, value 4 with probability 0.3, and value 5 with probability 0.4. And it says, what's the variance expressed to 1 decimal place? Let's see if we can work this out. We'll do it in R. Or first, let's do it by hand, and then we'll just do it in R. Okay. Let's see, switching the screen sharing is, let's see, what do I want? Okay. All right, so here's our PMF. It's X can take the values 2, 3, 4, 5, and it takes the values with probabilities 0.1, 0.2, 0.3, and 0.4. Okay, so those are the probabilities and those are the values. So the mean in this case, the mean is 0.1 times 2 plus 0.2 times 3 plus 0.3 times 4 plus 0.4 times 5. Okay. And then, so let's just show how to do that in R real quick. Or wait, let's derive the variance too. So let's call that, we'll call that mu, equal to mu. And then, excuse me real quick, someone's knocking at my door. Hey, I'm on. It's hard to get an uninterrupted minute around here. Let's see. Let's do the variance real quick too. So let's say that that works out to be mu. Okay. So how do we calculate the variance? One way to calculate the variance is that it's expected value of x minus mu squared. Okay. So we could do 0.1. Right. So this is going to be the sum of the probabilities, you know, of, let's say, pk times the potential value xk minus mu quantity squared. Okay, so we could do 0.1 times 2 minus mu, whatever that mu works out to be, we'll figure that out in a second, plus 0.2 times 3 minus mu, plus 0.3 times 4 minus mu, plus 0.4 times 5 minus mu, and I forgot my squares. So there's squared, 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 squared. Okay? The other way we could do it is that we know that expected value of x minus mu quantity squared works out to be expected value of x squared minus mu squared. Okay? So we need to figure out what expected value of x squared is. So that would be 0.1 times 2 squared plus 0.2 times 3 squared plus 0.3 times 4 squared plus 0.4 times 5 squared, okay? And then that quantity will work out to be, let's say, expected value of x squared, right? And so we would plug into this formula with expected value of x squared and mu squared and do it. Okay, so let's actually look and see what I typed in when I slapped this homework thing together. I need to figure out screen share, and then it's not letting me screen share again. But at any rate, if you actually look, since it looks like if you look at the answer, it goes through the R solution on that homework assignment, and it'll actually just show you really quickly how to do it in R. So the only functions you need are sum and then the basic arithmetic functions, the caret function for raising to the power and the asterisk function, you know, the basic arithmetic functions after that. So look at that to get the R code for doing that. And so I would just say, look at, you know, that homework problem basically shows you, I mean, almost exactly how to do that quiz problem. All right, let's see, where are we at? Question 8 and question 12 of quiz 4, inference. So let me get question 12, quiz 4. Okay, this question is not so bad. So double check, there was a typo in it, and so I corrected that early on. So double check that. But let me just talk broadly about what this question is about, and I'm hoping that you'll figure it out. Because this question should only take you 1 second. Okay, so when you do multiple tests all at once, right? The chance that you reject for at least one of them goes up with the number of tests that you do. If you generate a bunch of test statistics on the computer, let's say you generate a couple thousand of them, it wouldn't be surprising to you if one of them rejected, right? It wouldn't be surprising. In fact, you expect that 5% of them would reject if you're using a type 1 error rate of 5%. So this is fine if you want, sort of the average behavior to be 5%, but maybe what you want is your error rate to be such that the probability of at least one test rejecting is only 5%. Then you haven't controlled your error rate that way. You've controlled it if you were to perform each test in isolation without even acknowledging that you're performing other tests. Okay, so anyway, that's where this idea of the Bonferroni correction comes about. And it's basically this idea that if you're going to do a lot of tests and you want to control the probability of at least one of them being falsely rejected, then what you need to do is take the alpha rate that you would normally use, whether it's comparing your p-value to it, or calculating a rejection region, or I guess in principle you could even do this for a confidence if you did a couple thousand confidence intervals. You would take this alpha, the 0.05 in most cases, and you would divide it by the number of tests that you perform. This is called the Bonferroni correction. And then you would just use that alpha level for whatever you're doing. Okay? And so in this case, it says, you have a family-wise error rate of 5% and you perform 10 hypothesis tests. There's one small thing I would mention about this that might be causing confusion, and I haven't figured out a good way to fix this, but the question asks for a proportion, so make sure you're not putting in a percentage. So if it asks for a proportion, if you want to put in 5%, that means you need to put in 0.05, right? So at any rate, So double check if that might be the source of confusion. I haven't figured out, other than switching questions to multiple choice, I haven't figured a good way to do that. But multiple choice, it's too easy if you do multiple choice. There's no, anyone can take a multiple choice test and just kind of guess the right answers because they're always so yeah. But I appreciate and empathize with the fact that all this numeric short answer things have created a lot of problems. So one thing, at any rate, I'm confident you understand the principle, and I'm confident that you understand the procedure. And I'm wondering if maybe the small, if there's a mistake going on, if the small mistake is putting in a proportion rather than a percentage rather than a proportion. And this, because some of the other questions actually ask for a percentage, not a proportion. And so I don't know. I should be consistent, but at any rate, double check that. That might be the mistake that might be the source of the confusion in this case. And then question 2 and 3 of quiz 2 in boot camp 2. Let me look at those real quick. Also. Sorry, it's going to take me a minute to find it. Course page 3. So this was question 2 and 3 of quiz 2. And then I just realized I owed you a correction before, Rui. And I appreciate, Rui, all the questions you've been asking on the QA app here. That helps me do the office hours better. And I realized last time I said I was going to do something for you, and I forgot to do it. So I'll fix that thing now today. Okay, so question 2 and 3. Okay, so this is a neat problem. Okay, so let's see. Let me see. Question 2 and 3 of quiz 2. Okay, so the 2 and 3 don't exactly, from quiz 2 and boot camp 2, don't exactly adhere to the rest of your question. But let me talk about these in, question. Okay, I understand now. Okay, I think one thing that you're asking is, now I understand your earlier question. Okay, so what I'm about to describe is relevant for boot camp 2, but is not really that relevant for inference because I didn't talk about these techniques in inference. So in boot camp 2, we go over the chi-squared test. The chi-squared test, so how do we derive a chi-squared? The chi-squared is derived as the square of a standard normal. So when you square a number, you've thrown out its sign, right? Its sign is gone, okay? So if you were to do a two-sided normal test, right, you reject if your test statistic is too large or if it's too small, okay? And if you and then if you were to, so the way we phrase that is we say that the absolute value of the test statistic has to be bigger than, say, z1 minus alpha over 2. We discussed that earlier, okay? If you do the chi-squared version, you've squared that statistic and you've gotten rid of the sign. So we're only going to reject if that's too large, because if the original test statistic was either too large positive or too small negative, then its square will always be too large. Okay, we'll be looking in the direction of larger. Okay, so a chi-squared statistic, we're almost always, not always, but almost always looking in the direction of large chi-squared statistics as being rejections. So for that case, the chi-squared test is actually performing a two-sided test when you put alpha into the type 1 error rate. You don't have to divide alpha by 2 then, because what your test statistic is inherently testing two-sidedness to begin with, right? So it would be the same thing if we calculated the absolute value of the test statistic and compared it to, instead of the normal distribution, whatever the absolute value of a normal distribution is, the random variable being an absolute value of a normal distribution, then we would not have to divide alpha by 2, because we would want to control the type 1 error rate at, say, 5%. And if we do, and if we've removed the sign and we're appropriately calculating the distribution without that sign, then we don't need to divide alpha by 2. So I understand the confusion, and let me just summarize, okay? And the summary is something like this: if you have these settings that are covered in boot camp 2, like the square of a normal, the square of the standard normal statistic, the McNemar's test, which is a chi-squared type test, any of the two-group type chi-squared test from 2x2 tables that test things like odds ratios and equivalence of proportions, any of those two-group comparisons chi-squared tests, the test statistic itself is inherently looking at both directions, and so you don't have to divide alpha by 2, right? The reason we have to divide alpha by 2 when we don't look at the chi-square test, when we look at these normal tests, is because we have to account for the fact that we need the upper tail of the normal distribution and the lower tail of the normal distribution. But we don't want to even factor in the lower tail of the chi-squared distribution, because the only direction that represents towards the alternative in the chi-squared distribution for those cases is the test statistic being larger. So anyway, now I understand the source of the confusion. And that is confusing. I will grant you very much so that that is confusing. But if you want a simple rule, it's when you do the chi-square test for comparing two groups, you don't divide your alpha by 2. Okay, that would be the simple rule. But if you want, but I think we just talked a lot about the understanding behind the rule. But yeah, so anyway, I appreciate that that's confusing. Every time I teach this class, that comes up. And I appreciate that that's kind of confusing. And then I just want to note that question 2, just in case this was maybe a typo and you, this wasn't a typo, question 2 of quiz 2 kind of talks about odds and the derivation of odds, which doesn't have anything to do with this alpha question at all, the alpha or alpha over 2 question, so it's unrelated to that. And anyway, I just wanted to comment on this because it's a neat question. It basically goes down to how do you define, this question goes to how do you define probability. And one way to define probability is by this sort of gambling, these so-called Dutch book problems. And so you could define probability the way that we define probability in class, which is how frequent something occurs in repeated experiments, right? A frequency that's where you get the term frequency. So it's the frequency definition of probability. Another way to define probability is in terms of odds, like a subjective probability, not an objective probability, but a subjective probability. That is, I'm saying the probability is being how much I'm willing to bet that something will occur, and that how much you're willing to bet if you're a rational person then translates into a probability. And this was part of the early work on Bayesian thinking, was the idea of thinking about inference with respect to subjective rather than objective probabilities. So it's very neat. Anyway, and the problem doesn't ask any of that. The problem just asks, can you calculate odds from the, can you get the fact that the odds are what determines the payout in this sort of gambling experiment, in these sort of gambling settings. That's all. It's asking really more than anything just to churn through the calculations. But anyway, that's where it comes from. Actually, it has a rich history that's quite interesting, I think. Okay. Any other questions? I'll give people a minute. Those are some nice questions, Rui. You always seem to have nice questions for the office hours. And I appreciate everyone taking the classes, and especially if you're in inference right now, putting up with all the foibles from the quizzes. I appreciate all the feedback people have been giving me, and that's helping me improve the class, and hopefully the next run, next month, will be going a little bit smoother. But at any rate, since I don't see any more questions, I'll end this office hours. I'll have another one next week, I think. I'll have to double check my schedule, but I probably will have another one. And again, thanks everyone for taking the classes, and look forward to seeing you on the forums.